Hi everyone, my name is Ashish. I'm a PhD student at the University of Limerick under Dr. Jim Buckley from UL and Dr. Andrew Laguerre from Horizon Globex. In this presentation, I'm going to talk about the interesting intersection between software engineering and blockchain. We take a look at how existing software metrics fare in blockchain systems. Blockchain-based systems are an interesting example of systems with operational constraints. Before I dive deep into our investigation, I will give a brief overview of what a blockchain is and how it relates to software engineering. I'll also talk about Solidity and describe the aim of the study. Then I'll talk about how software metrics relate with smart contracts, followed by an overview of our study design and then the description of our results. The term blockchain was popularized by cryptocurrency Bitcoin, specifically during the crypto economic boom of 2017. Blockchain as a technology allows for decentralized execution of instructions. In Bitcoin, like cryptocurrencies, the computing instructions are limited to only financial transactions. Every transaction on Bitcoin is stored on a global ledger maintained by a geographically spread out peer-to-peer network. This ledger is tamper-proof as the data stored is immutable in nature, that is, changing a transaction in past is not possible without modifying every transaction after that. This is computationally expensive. Bitcoin's computing engine was not Turing complete, thus limiting the functionality of the system. Newer blockchain systems such as Ethereum implement a Turing complete instruction set over the blockchain. This allows for decentralized execution of any computing script on a global computer that is tamper-proof and not prone to denial of service attacks. This new execution environment provided by Ethereum executes computing scripts known as smart contracts. These smart contracts are often written in high-level object-oriented programming languages such as Solidity. These smart contracts are capable of performing complex intermediary tasks related to financial services, such as allowing peer-to-peer betting. However, as these smart contracts are often associated with monetary value, it is crucial to design high-quality smart contracts, which is a core motivation of the study. Solidity was designed with both syntactical and conceptual similarities to traditional object-oriented programming languages such as C, C++, Java, and JavaScript. However, there are a few major differences between Solidity and conventional object-oriented language. The foremost of these being the immutable nature of smart contracts. This immutable nature makes post-deployment patches near to impossible, thus putting a high emphasis on testing the smart contracts prior to deployment. Another interesting aspect of blockchain is its decentralized nature. There is no single party handling all the transactions and smart contract executions on the network. All the computing instructions are executed by a peer-to-peer network. To ensure that the system remains safe, blockchain provides an incentive for honest behavior. This incentive is in form of native cryptocurrency. Every instruction executed on Ethereum carries an execution fee known as gas. This price of gas is dynamically adjusted by the Ethereum network. There are two main costs involved with deploying a smart contract. The first one is deployment cost and the second one is execution cost. The author of smart contract pays deployment cost once, whereas the execution cost is paid over every execution cycle. This integration of market-driven execution cost differentiates smart contracts significantly from traditional programs, as the aim here is to minimize the overall cost of smart contract. In this paper, we aim to explore the quality of smart contracts in the context of cost and design choices. With the differences in execution environment and the nature of cost associated with the execution, we aim to capture if developers move away from our conventional object-oriented design practices to a more smart contract-specific practice set. In this early research, we intend to measure this by only focusing on inheritance-based metrics. Now I will describe the metrics followed by how we apply these to smart contracts. Inheritance is one of the most widely used object-oriented technique that supports code reuse. However, inheritance also has a downside. A high degree of inheritance can increase the overall complexity of the source code. This complexity has been linked with more faults in traditional systems. In traditional object-oriented programming, this adverse impact has led to the paradigm of composition over inheritance. The relationship between inheritance and complexity makes it an interesting topic in the context of smart contracts, as the security of smart contract is of paramount importance. Once deployed, the authors may not be able to fix any faults in the source code, which may result in loss of monetary value associated with the smart contract. In our research, we primarily focus on inheritance-based metrics proposed by Chidambra, specifically depth of inheritance tree and number of children. Depth of inheritance tree calculates the maximum length of a path from a class to the root class, whereas the number of children indicates the number of immediate subclasses that depend on a class and a class structure. To better explain this concept, here's an example of depth of inheritance and number of children calculation from our sample set. Here we can see an inheritance tree diagram of a CRO contract, which is based on an ERC20 token. In this example, we calculate depth of inheritance by following the longest route from leaf to root node, and the number of children is averaged through this run. In this slide, we have two code snippets of functionally identical Solidity smart contracts. The snippet 1 shows an example of inheritance, whereas the second snippet uses a workaround composition where we can see how we have reused the contract display within our contract request. We use these functionally identical smart contracts to calculate the cost associated with either picking inheritance over composition or composition over inheritance. In table 1, we can see that inheritance significantly reduces the cost of deployment while also resulting in lower cost of execution. The savings in the cost of execution accumulate over time and make inheritance the most cost-effective of these two techniques. Based on our example and the cost-oriented reasoning, we present two hypotheses. The first one is that developers will favor higher depth of inheritance to limit the cost of deployment. And the second hypothesis extend this cost-oriented reasoning by focusing on the cost of execution, suggesting that developers will favor a low number of children per class. This is due to the cost associated with function calls. If you have more child per class, that implies more functional dependency and higher cost of execution. Now, I will briefly go over the design of our study before diving into the results. All the smart contracts deployed on Ethereum are open source by the nature of deployment system. However, we only have access to Ethereum virtual machine specific code and not Solidity. There are a number of open source decompilers, however, reliability of these tools is beyond the scope of our work. Thus, we rely on smart contracts that have publicly available Solidity source code. We can easily verify the Solidity source code by comparing it with virtual machine specific code present on Ethereum. We only select smart contracts with market capitalization of over 5,000 US dollars. We extract these smart contracts using Etherscan API. In total, we obtain 229 Solidity smart contracts. We verify the smart contracts for accuracy. After obtaining verified Solidity code, we use a static analysis tool by Higdis to calculate the value of depth of inheritance. However, the value of number of children was manually calculated through generating inheritance tree diagrams of all the smart contracts. Now, I will walk through the results of our study. We report that smart contracts on average tend to have high depth of inheritance value of 3.29, with 7 being the highest value and 0 being the lowest value in our dataset. In contrast to traditional systems, smart contracts tend to have higher depth of inheritance to line of code ratio. We report an average depth of inheritance of 3.29 per 328 lines, which is significantly different from traditional systems where Tang et al. Reported depth of inheritance value of 1.25 per 5.6 thousand lines, 1.54 per 21,000 lines, and 0.89 per 16,000 lines. One interesting observation from our sample is violation of object-oriented paradigm, with 4% of our sample reporting no inheritance at all. However, overall smart contracts tend to have higher depth of inheritance based on our sample. This is in line with our hypothesis 1 based on the cost of deployment rationale. Another surprising finding is related to the number of children, where we find that the average is 0.99, which again is against the guidance of Chidambra for object-oriented programs, where they say more children allows for more reuse. a core rationale for inheritance, and thus more children are envisioned. However, this is in line with our hypothesis too that suggests a lower number of child based on cost of execution rationale. To conclude, as software tends to vary a lot depending on deployment environment, a single set of metrics may not be suitable for all environments. We demonstrate this by looking at inheritance-based metrics for smart contracts, where the cost of execution and deployment seem to skew developers away from conventional design practices such as composition over inheritance. In future, we intend to conduct the experiment on a larger dataset using a custom-built static analyzer. We also intend to explore other software metrics to examine smart contracts. Thank you for your time.